For this problem we need to find the voltage V, which is this one, and we can see that there is an independent current source, an independent voltage source, and a current dependent voltage source, this one. So this is what we have, and we have to apply node voltage method to solve this problem. So we can see that this node has the most elements here, so we will call this the ground node, and then this is another node there which we can label the, let's call the node, I don't know, let's label the node voltage there, so that's, let's call it V1, and then this is V because that's V. This voltage rise is V, or this drop in downwards is V, so this voltage has to be V at this node. And this is a current dependent voltage source, so we call this thing as a super node. So we because there is a source between these two nodes, it can be a dependent or can be an independent source, doesn't matter, but we consider this whole thing as one node, and when we do that we call it a super node. So since this is V and there is a rise of Ix, so voltage of this node will be V plus Ix, that is we know. So what we will do, we will try to write the node equation for this super node first. So we have, let's label all the currents at outgoing current. So V minus V1 over 2.5 will be the current in that direction. The downwards current will be V over 10. Then we don't write anything for this one because this whole thing is a node. That's the thing. So we write again downward current here, which will be Vi plus Ix, because that is the voltage of this node, over 2.5, and then finally this current as going there outwards, that will be V plus Ix minus 10, because that's the, and divided by this resistance which is 1, and there is no inward current, or coming towards the node current is 0, so we will just write 0 there. So this one I can write now, rewrite, so I will just write them as fraction, and so 2.5 plus 1 over 10 plus again 2.5, 1 over 2.5, and then we have plus 1 there, and then minus V1 will be, the coefficient will be actually let's say plus, and that's minus 1.25, and then we have 10 there on that side. We have this one plus Ix over 2.5. Ix is another variable, but we will see something soon, and this one is equal to 10. The 10 here is a coefficient, is a constant which goes on the right hand side. Let's leave it like that, but we have to recall what Ix is. Ix actually can be written in terms of V1, not V1. So V1 will be Ix into 7.5, Ix into 7.5, that is the voltage drop across 7.5 volts there, and Ix is the current downwards. So what we, instead of, so here it seems there are 3 variables, but it's not, because Ix can be written in terms of Vx. So what I can do here is, instead of Ix I can write V1 over 7.5. so that's what I will do. So there's some correction here. This voltage is actually 12 volts, not 10 volts, so I will rewrite that. But bigger problem is what I have when writing this line from that line, I missed one thing. So Ix over 2.5 plus Ix, there were another term for Ix because there are 2 Ix basically. So yeah, just that. and this becomes of course 12 because that was actually 12. So okay, so this is what instead of ix we can write. So again going back there, so that will be 1 over 2.5 plus, I'm leaving like that for the time being, plus 1 over 2.5 plus 1, and then instead this is plus v1 which is minus 1.25, and then instead of ix what I can write is so ix basically is plus ix is 1 over 2.5 plus 1, and that's equals to 12. So instead of ix what I can write is v1 over 7.5. So that becomes now as 1 over 2.5 plus 1 over 10 plus 1 over 2.5 plus 1, and then plus v1 is minus 2.5 plus 1 over 2.5 into 1 over 7.5 plus that was just ix, so 1 over 7.5. So basically what has happened, instead of ix I have written v1 over 7.5, and that 7.5 is multiplied by this 2.5 here, for that term is coming from there, and then ix times 1, that would be just 1 over 7.5 because v1 is outside there. So that's a bit clumsy, but that's what. So there are basically this one is just, so that's 7.5 times 2.5. So 1 over 7.5 times 2.5, and then plus 1 over 7.5 equals to 12 there. And so that's one equation. And then we have another one which is for V1, that node, we can write KCL for this node. That will be 4.8 is entering, so we can write that on the right hand side. We will do that later. But initially V1 over 7.5, so that's a simpler equation, V1 over 7.5, and then plus V1 minus V over 2.5, and that's equals to 4.8. So this is now becoming V over 1, V times 1 over 2.5 plus V1 is 1 over 7.5 plus 1 over 2.5 equals to 4.8. This is our second equation. Now what I have done here is so this is the first equation. What I have done here is I have put this whole coefficients in a linear solver, and I have got the result. So I won't do the solution. It's just algebraic, just fraction addition, and then just solving simultaneous equation with two unknowns. So two equations, two unknowns, that should be fine. So the result that I got for V is, so V I got 8 volts, and then V1 I got 15 volts. So I needed to find V, which is 8 volts. Now what I will show here is, I will before finishing this video I will quickly show the determinant method of solving simultaneous equations. So let's say we have one equation, a1x plus b1y equals to c1, and then we have another equation, a2x plus b2y equals to c2. We need to solve them. These a1, b1, c1, these are all constants, a2, b2, c2, and x and y are the variables, the unknowns, which will be for node voltage method. These will be two voltages, basically two unknown voltages. So the way to solve this is, we can write x here, just determinant method, and we will write in the denominator, we will write a1 a2 b1 b2 like that, and the numerator will be, since we want to find x, that will be c1 c2, and then here we will have b1 b2. So since we wanted to find x, instead of x we have written this one. Similarly y will be, the denominator will be same, a1 a2 b1 b2, and then we will have a1 a2, and here we will have c1 c2. And what we do from there I can show for this one y, because I have written this later. So this will be just a1 b2 minus a2 b1, and here it will be a1 c2 minus a2 c1, and then just this addition, subtraction, multiplication, then subtraction, and then whatever, then division. That's what it is. So instead of like trying to eliminate one by multiplying one, we can do this one. This is more straightforward. So this is something. And even when there will be three unknowns in node voltage method as well, we will see that probably, hopefully, and then we will have three simultaneous equations, and then it will be very difficult to do the elimination thing. So then we actually have to do the determinant method. So then we have to adapt that. There will be there's just, it's now 2 by 2 matrix or determinant, so 2 column 2 row, but when 3 variable, it will be 3 columns and 3 rows. So it will be similar, though we will do that later, but this is a better way, this is a more straightforward way, and so we can do that. And I would request you to do this problem as well using this method. What I have done here is I have just put this whole thing in a linear solver in a software, and then I have got the results, and I have just written directly the results.